Hello and welcome back to compiler programming. Now that we have implemented the deferred encoding of instructions for functions, I thought I'd spend some time on doing minor optimizations for the generated assembly. If we look right now at what it looks like when you run code, the resulting stuff is quite verbose to say the least, and it's not at all what a good compiler would generate. And while I want to leave hardcore optimizations for later, I just wanted to show a bit of what it looks like, right? Because I always say, oh, it's fine, we can like deal with it later, and we don't care about optimization, but it's also, I think, important to show like what it would entail if we were to do some of them. And I just want to pick like low-hanging fruit, which will already give us, I think, quite nice results. Let me show you what we have right now. So we have kind of a snapshot and know where we are and where we want to be. So let's go into the call. So this is implementation of a Fibonacci function. And there is a lot of stuff here. One thing that is kind of standing out is a lot of the instructions have this gigantic list of zeros at the end. And this is just connected with the fact of how we are encoding the operands, especially immediate operands. So if you look over here, we're just doing RSP plus 78, but we use the whole 32 bits here just encode 78, and then we use another 32 bits for the comparison, and that's just not very nice. And there is a bunch of stuff like this all over the place. And I want to start actually with the canonical example of the optimization that every compiler makes for x86 architecture, because there is no zero. If you want to zero out a register, you end up with this kind of stuff, and that's not what you want to have in your program. In general, the reason this matters is because these are just bytes in memory, right? And when the processor executes your program, it has to load these bytes from memory, it has to decode them, and then it has to execute them. When it loads it from memory, it stores it in the instruction cache, which is quite small, level 1 cache, but separate usually from your data, at least I think on modern processors. And basically, the bigger the code of your program is, the less of it fits into the cache. So it means that the more a processor has to do cache eviction and reloading from memory, and reloading from memory is really, really slow. And this is actually also why some of the jumps can be pretty slow, because if it doesn't know where it will go, it can't prefetch all the instructions, and like it just becomes a nightmare. This is why tight loops with little code is generally preferable. Okay, let's do this move array x 0. This is a pretty simple optimization that we can add, and I believe we even have a comment to do that. So if we look here at move value, maybe I have removed this, but here's what we can do. So this is for movies X, which is actually also something we need to implement now, and this will be a nice optimization by itself. In fact, like zeroing a register could also be a moves X, which will be shorter than what we have right now, because we could use like a signed extend move of 0 byte into a 64-bit value, and that's that's already good, but I said the canonical example is even shorter. So here's what we are saying. If B operand type is operand type immediate 64, this is going to be quite a big if, but this is what all optimizations are about. Basically, whenever you're trying to optimize a compiler or trying to implement, not optimizing a compiler, but implement optimizations inside the compiler, it always devolves to the same thing. It's going through the source code or bytecode or whatever and picking out particular patterns. In this case, what we are looking for is a pattern where we have a register on the left side and a 0 on the right side. So like we are moving 0 into a register, but it doesn't really matter if what is the size of the immediate as long as it's 0. And so we will, like I said, this will be quite big if. So we say if a operand type is a register, and then we have a nested set of conditions here. So like this, we just say return, and instead we will encode a new instruction, which we will need to also create the encoding for, but we can do that. So we do XOR a operand. And just to show you that this is what happens, if you go to disassembly here, see this instruction, XOR ECX. So if you look at our source code, we are doing this call, f of 0, and we know that 0 is, that the first argument to a function goes into C register, so because basically RCX, but because of how assembly works for 64-bit architecture, you can omit the R prefix for this instruction, but in general, this basically means put 0 into ECX. That's what I'm trying to say. And this is exactly what we have here, and this is exactly what we are trying to implement, which is XOR operand. And for now, I will not do this optimization that can drop the 48 prefix, because that requires a bunch of hoops to jump through. So we'll leave that for later. So immediate 32 or immediate 8. And since we already checked that the size actually matches, actually we could probably move this check now into here, but that's fine. Okay, so we say the left side is registered, the right side is immediate, and the operand immediate 8 is 0. I can compare, actually, no, we have to do it like so. Immediate 64. Yes, I have to redo this a bit. 8, and 32 and 32. And we can decide honestly where we want to stop, right? Because we can say, maybe actually if you have immediate 8, we're just gonna do a move. Because move technically does not I'm not sure how deep I want to go into it, but basically move uses different part of the CPU than the XOR does, although it might be that the CPU itself has a special condition for this instruction. because I think I also mentioned at some point that what you write here, this assembly, is not what processor actually executes. It reinterprets it into even lower format that then it uses to run your code. So it is possible that it actually has a micro operation that says actually zero this register. I don't know. Anyhow, this is what we have. A register on the left side, zero on the right side, and we XOR the A operand with A operand. So now we're gonna need Firefox because we will need to look up how XOR actually is encoded. So let's go to XOR. And right now I'm only interested in this version of XOR. So this is what we will do. Let me grab the instruction and we can put it somewhere. I'll put it next to inc because they are actually all instructions on numbers. Okay, XOR. What is your encoding? You have 33, then it is underscore R, and then RM16. That's good. I can replace this stuff, this stuff. Okay, so we have this version, and if we want to have an 8-bit version as well, we can do that very easily. We just say R2, R, and RM8. If you pay attention, you probably notice that a lot of the times when you have this pattern where for the byte operands you have one number, and for 16, 32, and 64 you have basically +1. You have it here, you have it here, you have it here. So like it's a very common pattern, and I believe that at least for all the instructions it holds almost always true, that like you just use the first bit to encode the size of the operand, which is kind of neat. Okay, XOR, 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 more XOR, and more XOR. Okay, so we have the instruction, we have our test, and we can try to build. It builds just fine. Let's see if it works fine. Okay, start. And we already are in trouble because let me make this larger. Function spec, encode instruction, function end. Yeah, now actually this is gonna be a bit of a problem for us because so previously we could easily trace where the instruction we are encoding actually is coming from, and now it is no longer the case. So maybe I will make another video later about how to deal with this situation. How can we trace where a particular instruction comes from, so we know if there is an error, where to look for the issue. Right now I can figure this out because we can jump to the right thing, but in general that's probably not the case. Okay, so what happens right now is it tries to call this size of S32 and size of S32, and it we put 0 into the first argument, so naturally we get this XOR, but it says it did not find an acceptable encoding for R64, which is kind of strange. Yeah, okay. Yeah, I'm completely spaced out on that. This is not what we want. We want it to be like this. So are correct our assertion. I was wrong. Good. Let's try that again. It looks like we actually have a issue right now, so something did not work exactly right. We can take a look at that, but I still want to look at the function. And oh, okay. So I think the issue right now might be that we are doing, actually no, let me go check it here. So we still have move rex 0, which is kind of weird. So it looks like our check did not work correctly for some reason. But it did work in other cases. So we do have XOR array x here, and okay. Actually, this might be a problem. And yeah, I know why this failed, and this is actually another reason why these optimizations are a bit finicky. So what happens is when you do XOR, it actually changes the flags, changes the comparison flags. So this instruction, it does the comparison, and as a result, if you look over here, there is this if flags register. I think I can enable flags separately. Yeah, so there are these flags, and if I step through this code, so after this compare, you look over here and the flags will change. See? So 0 flag is set and whatever. It's super weird that Visual Studio does not name the flags like they are named in the processor. Like, I have no idea why they did that, but it doesn't matter. The point right now is that if you watch after I do XOR array x, the flags will actually change. Or, I mean, in this case, I don't, because they are exactly the same, but they might change, and I believe this is exactly what happens in here. My point is that our, like, we use array-x a lot, and we clear it a lot, and because we sometimes clear it after we did the compare, we cannot actually use XOR because it will mess up our stuff. So our whole optimization is not gonna work, and this is not what we're gonna do. So instead, let's fall back to previous idea that I had of using MoveSX. And this is kind of should also work, I think, because basically the idea would be that instead of, so we write a comment, we can not use that in general case because it messes up flags register. Yeah, that's fine. So instead, I will do movesx, and as b operand, I will say that it's gonna be immediate 8 of 0. So this also should produce the same result. If we look at movesx, then but movesx only accepts register memory, which is kind of not very nice, I guess. If I look into move, is there a signed extended move here? No, there isn't one. That is kind of unfortunate. What can we do? What can we do to help with this? I guess we can change our code that deals with the comparison to do something else. I mean, all of these instructions, they accept register on memory. So instead of putting it into, instead of putting result in arrayx, we could just shove it directly on the stack, and then this would work. Okay, let's try that. Maybe we should change a node then to comparisons need to be aware of this optimization. And this is kind of the whole thing with optimizations as well, that if you add them, you suddenly have these weird dependencies in your applications, so that slow you down, and this is why you usually would want to leave them off till later if you can. But I still want to show the guys this, so let's stick with it. Okay, we have compare, all right? So this is our compare code, and let's just look what it does. It does the comparison, that's fine. And then here it clears the register. But because we are using this register for the compare, we actually cannot really use XOR as it states here. So instead, what I will do is I will change this. I will remove this stuff. So we're no longer going to use register A for storing the value. We're no longer going to use it for the result. And instead, we're going to put this result on stack. So we say value star comparison result is reserve stack of builder and descriptor as 8. We use this stuff, and then we return. It's actually very interesting. Why does our compare return a 64-bit value? This is another sort of an interesting thing. It should actually return this byte. And because we already reserved stack for it, we don't really need to do that again, and no need to do a move. So in a sense, if all of this works, then we will also have removed a bunch of unnecessary instructions. But let's see. Let's verify our logic. We compare, then we reserve stack, and then we use one of these instructions, set z, set l, whatever, to put to set that byte to what we want. That looks good to me, but it might generate a bunch of other issues for us because we bookmark actually this. I want to undo our change to move value for now, remove this optimization, because we are changing a different part of the code, and it would be nice if it wasn't affected by the stuff that we're doing. Okay, let's run the test. Interesting. So this comes from inside the if, because now the result of our comparison is a byte. We need to change if to compare to a byte, and we expect basically a boolean to be byte sized. So let's check that. Okay, it still did not have the encoding, but let's check. Compare. Yeah, there is no byte version of it, but this is something we can fix very easily. And this is the version that we want, rm8 im8. So let's add that. It's 80 again. See the same pattern, 1 here, 0 here, so like +1. rm8 im8. Let's check again. Okay. So this is interesting. We have somewhere comparison between R64 and immediate 8. Okay, let's check that. This is inside of this main spec. Reflection. This is the Hacky Code for tagged unions that I wrote at some point. And if I were a betting man, I would say that the actual issue is here, because we probably use, yeah, I guess. So let's actually run this in here and see what is going on. Yeah, did not find acceptable encoding, that's fine. What is the actual instruction that you're trying to encode? So the register is B. Interesting. Okay, so this is this register, and comparison is from I'm a bit confused. Okay, what is the tag value? Tag value, value operand register. Is this was it indirect or was it direct? Instructions, operands. Now this is directly a register operand, and it is directly a compare. We return this result value. And this is the comparison, compare equal, tag value, value from 64. What is the immediate operand? Immediate operand is 0. What is that? I. So it could be this, I guess, but no, not really, because this is a tag value. And we are looking at something else. So where again is this? Maybe cast to tag. Oh, okay. So this is what happens, yes. Here we cannot do this, at least not in the semantics that we have right now. So instead we have to say that so here's what happens. We get either the pointer to the value inside the tagged union, or we get a null, and then we check basically here if it is a null or not. But right now I cannot do comparisons with 0, and we can actually check how Compiler Explorer does those comparisons to 0. Maybe there is a better way to do it than what I'm doing right now. So let's say here I have char star, and I say if bytes return 0. It does do comparison to 0. That's kind of interesting. Does it do that if I do optimizations as well? Or it does something else? Actually, it should be OX. Come on. Visual Studio Compiler. It does test. Interesting. What does test do? Test. Logical compare. Computes a bitwise logical AND of the first operand and the second operand, and sets SF, ZF, and PF status flags according to the result. So basically, if we are using inside of an if, we use JZ, which basically uses 0 flag, and since this thing uses a 0 flag, we could totally use test to implement our thing here. I mean, why not? We can do that, I guess. Let's try. So comment this out, mark this line so we don't forget where we are, and do this. Tests value operand, value operand. Although this might present a problem that the operand, like we can't have, if it's a memory, it will be an issue. So can I do compare with a sign extended byte? Or not really? No, not really. But what I could do is have a special immediate that is gonna be the right size for whatever we are trying to compare to. So here's what I'm gonna do. I'm gonna say U32 byte size. Byte size is a descriptor byte size of value descriptor, and we say if byte size, or how do I want to do it? If byte size is 4 or byte size is 8, then I'm gonna do this. Else if byte size is 1, I'm gonna do something else. So here will be 32, here will be 8. And I can use 32 for both 64 bits and 32 bits because it is going to be signed extended. And otherwise, I have no idea what he gave me. And I just say unsupported value inside if. Okay, it fails, but it fails because we are still running. So let's rebuild now and check again. Cool, so this seems to work. We now have optimized our stuff inside of compare, which actually is kind of nice. Okay, so we have less instructions here. We can remove the comment about XOR because we actually can't use it here. We still have a bunch of stuff to do. Operand size, right. This actually uses correct operand size. So another to-do goes away. And we can get back to the original thing that we wanted to do, which was optimizing, setting something to 0. Actually setting a register to 0. So let's try that again, now that our if that no longer should be relying on the ArrayX stuff. So let's try that. Let's go back to the function spec so we can look at our Fibonacci function. This right around here, we do start, and I don't want to make a pause here. I want to make a pause over here. So far everything looks fine. So it seems that at least we fixed that issue with so XOR was a problem before because of comparison. Now it doesn't look to be. And we can now look at the disassembly. Go into here, we jump inside, and we can see what is going on. Cool. So we have this XOR now, which is pretty neat. But we do still have some we still have this. So what is this all about? Is this part of comparison for some reason? Like, do we have move that is immediate 64 of 0? Like, what's that? I'm very, very curious now. So let's just take a look at the stuff here. Yeah, so if I look at disassembly again, and we look at the function, it probably is this stuff where we come like yes. Let's look at what compare does again. So it creates a temp B, and then this temp B is So here's what's going on. Let me go to move value. What's going on is we end up in this case, and because we are doing here things directly, we don't take care of this optimization. So what I will try to do, and I'm not sure if we will end up in an infinite loop, which we shouldn't be, I will, instead of directly push instruction, I will say move value reg a b, and then I would say move value a reg a. Yeah, this is actually not really true. We are considering regs to be volatile. So builder, forgot about that. Okay, that builds. Let's see if that works though. Start. Disassembly, and go inside and check on the call, and look at that. We have XOR rex, and then we are moving it around. So this is pretty neat. Like you see that XOR is pretty small instruction, right? We just 3 bytes, and in reality, as I said, it can be like you could drop this, but it relies on a certain knowledge about how x86 stack works, and I don't want to do it right now. But one final thing I want to look at is now majority of zeros, except for this one, which could also be optimized. And this is very interesting, right? So maybe the only thing I will do for now is just discuss this one. We are in a bit of a predicament here. The issue is this is obviously not optimal. We have a lot of zeros in here, and it's not great. Now, we could do several optimizations looking at this. Optimization number 1 is we could totally shrink it to 32 bits, as I said, because it will just sign extend the 64-bit 32-bit number to 64 bits, and it will move there. And this is maybe what we will do because it is a very, very safe thing for us to do, except that it requires us to know if a number is signed or not signed. Okay, what else could we do here? Well, we could actually split it into 2 instructions. And this is why if you look at your compiler stuff, so at least in Visual Studio Compiler, there are these optimization flags, and OX says, I want to optimize for speed. But you can say OS, and in this case, it will be exactly the same thing. But OS is actually, interestingly, it's not. I wouldn't have expected that. But I believe maybe I'm messing up the flag, but there is a flag that says I want to optimize for size. And they, yeah. So here is the favor small code, favor fast code. So actually it needs to probably go into like this. OSOX. So again, I think in this case, it will be exactly the same because the smallest code is also the fastest, but it's not always the case. And this kind of situation is exactly that. So I could totally do this XOR, and I said, especially if we drop this prefix, we would end up with 2 bytes to zero it, and then I could do inc instruction, which is, especially with arrayx register, inc instruction is probably 1 or 2 bytes. So we will end up with 4 bytes to make this happen. But it does execute 2 instructions. So in a sense, it's probably not the fastest thing, but it is the smallest thing. And this is always this tricky juggle when you do any kind of optimizations to decide how you want to handle it. So just some food for thought. Let's say that. I guess we could do this optimization for the numbers that we know to be positive. So let's do it. Again, inside move, again with immediates. And now what we say is that if this stuff, if B operand type is immediate 64 and B operand immediate is, I need to treat it, do I need to treat it as, no, I actually don't need to treat it as unsigned. So if it is less than or equal to 0x7ff, I really wish that they would add this stuff in C, these separators that are now in C++20, I believe, and a bunch of other languages. So nicer to be able to do that. Anyhow, so this number might look weird to you, but if you convert it into binary, it is gonna be 0B0 1 1 1 1 1, bunch of ones, yeah, and then ones all the way. So like it's all the ones there, and basically because this bit is 0, then we know that it's a positive number. We can't just check that it's a positive number. We can't just say like more than 0, right? Because it is 64-bit. I could do this comparison other way, like I could convert it to 32 bits and then say that it's more than 0. Guess maybe that's nicer to look at. So let's stick with that option. But essentially, this is what we are trying to do. My point is, you can't do this check without either this weird constant or this conversion, because it will give you the wrong result. Okay. So if this is the case, then we actually switch out the stuff and we say that what I actually want to do is I want to, again, this is going to be a recursive call because we might have nicer optimizations. We move to A, immediate 32 of whatever was B operand, immediate 32. Cannot convert operand to value, so it's a value from S32. Okay, let's see if that works. It does seem to not blow up in our face. So let's take one final look at the assembly, marvel at how much shorter it is, and wrap up today's video. Good. So, as you can see, now this move arrayx1 is 4 bytes shorter, which is a pretty good win in my book. And we have XORs that made it shorter, so it's kind of nice. Okay, that will be it for today. I wanted to give you a short look at what optimizations can compilers implement when they are encoding instructions. I'm also pretty happy that we ran into the issue with XOR because I was able to discuss why the optimizations are problematic and why they make your program very complicated, especially when this is a compiler. And that will be it for today. I thank you very much for watching and hopefully see you next time.